Cool. So again, everyone, welcome to Paper Club, brought to you by NPlan. This week's discussion is going to be led by Dan. Dan is a data scientist at NPlan, for those of you who don't know him already. He's going to be speaking about cross transformers, which is a very recent paper which addresses a very interesting problem, which they call supervision collapse. Is that it? Yeah, supervision collapse. Which is basically that a model learns only what it needs during training, and then it forgets everything that it might need for generalizing. So I'm going to let Dan take it from here. Go ahead.
Cool, thanks, Carlos. Yeah, so hi, everyone. I'm going to be talking about this paper that Carlos has just introduced, cross transformers, which is an accepted paper for, I think, NeurIPS 2020. So I'll just share my screen and we can start talking about it. Cool. So is that all right? Can everyone see that? Yeah, cool. So as Carlos says, it's quite an interesting paper about a problem with, classic image classification, which is that it struggles to generalize to new problems and new situations. And so, yeah, they introduced a couple of useful tools, I suppose, one being a new architecture and one being a new training technique that sort of try to mitigate some of these problems and make got a chat thing already. Make a make a network that generalizes a little better between problems. Okay, so first they basically start by introducing the issue, as I've just done there, and then they move on to talking about the specific data set they're actually going to use, and they use this data set called metadata set, which is it's got ImageNet as the sort of base to it, but it also has several other image classification data sets that are like adjacent to ImageNet. So I got the paper here and it sort of says which data sets are in this metadata set. So it's ImageNet, Omniglot, aircraft, a birds data set, textures. So yeah, all of these data sets are within the metadata set, and the training happens on a subset of ImageNet, and then the test is to see how well you can generalize to the data in these 9 other data sets and the subset of ImageNet that you did not train on. And the way that this problem is sort of framed is to talk about episodes. So each data set might be an episode, and a different episode indicates that you might have a different distribution for your data. You might have a different set of classes, and so the challenge is to make it so that your pre-training and your architecture makes it so that you can quickly generalize to a new episode without needing a huge number of labeled data, or basically retraining your classifier from scratch to just classify on this new data set. And so the way that words that they use at this point within an episode, you've got a support set, which are the data that you use to try to transfer your knowledge about this new data set across to your network. And you've got the query set, which are the images that you test on from this data set. Okay, so that's metadata set, and that's basically what the paper is structured around. And the state of the art before this paper is something like a prototypical net. So that is it's a network that produces an embedding based on an example, based on a query image. So you'll have your images from the support set. Perhaps this example on the left is kind of interesting to look at here. So the colored circles are the images from the support set. And so we can say that we can see that in the embedding that has been made by this network, all of the images in the support set are close together. And so you make a prototypical embedding for this class by taking the average of the embeddings for all of the examples within the support set for that class. And you do the same for class 2 and class 3. And then a query image would come in and you'd say, okay, which centroid is this closest to? I can see that it's closest to the C2 centroid. And so I will classify this query image as a C2 class. And yeah, the embedding for a prototypical net is optimized in this way. So you'll have labels for your query set, and you want to optimize the embedding so that this distance-based classification classifies the most query examples correctly. And yeah, I think that they do that with Adam, just a descent-based approach. So that's the state of the art, and they say, yeah, this is achieving like 50% accuracy on the ImageNet classes that they're not training on. So and they say, well, if we trained on those classes, we'd be way more accurate. So what's going on here? And yeah, here's just a illustration of the sort of lack of accuracy or the confusion that's befalling this type of network. So here are some query images from the unseen portion of ImageNet. And on the right here, these are the nearest neighbors of the embedding of this query. And we can see that they're not really relevant for the most part. So we would end up classifying this image as something that it's not. So yeah, this knot is being classified as like a reptile of some kind. Bassoon is being classified as a letter opener. And these two different types of screws are falling in completely different categories. So we can kind of see that we've ended up getting embeddings for the types, for the classes that are within our training set, but not really managing to get any kind of generalization as to what is semantically similar to our query images, right? Okay, so I think Adam's asking, when they say embedding, they basically mean the features that are the output from an all but last layer of, for example, a ResNet. Yeah, so that's it, basically. They use just some neural network, and I think it frequently is a ResNet. They do provide implementation details in the appendix. Sorry, let me just take a little look down. Yeah. So I'm pretty sure, I can't see it exactly now, but I'm pretty sure they just use a ResNet.
Yeah, so I think that with with these centroid-based algorithms like prototypical nets, basically what you want is an embedded representation, which I mean, embedding is a very generic word. We tend to say embeddings for text embeddings, but you can get an embedded representation for an image as well. So yeah, however you reach this different representation is up to you basically.
Yeah.
But yeah, then what prototypical nets do is they, instead of using that embedding for classification, like putting a softmax layer on top of it, they just do some proximity to a centroid.
Yep. Cool. Okay, so that's the problem. And basically, we're not seeing generalization from like actual parts of the image. We're not seeing semantic similarity from the query image to the things that we're classifying it with using a prototypical net. And so to try and solve these two problems, they suggest. So sorry, Ben's just asked, when they talk about domain shift, do they mean a shift in the domain of the embedding? I think what they mean is a shift in the distribution of data. So yeah, if we look at this example, you know, our data that we trained on, it was hammers, it was these Buckeye things, like a conqueror, I guess, letter openers, and Gila monsters. So, and the data that we're testing on is distributed very differently. It has all these new images, new types of image. Does that sound fair,
Yeah.
Carlos?
Yeah. Just to add, it's also about the well, for images in particular, you can think of domain shift. If your classes are screws, for example, if all the screws in your training set, which can be ImageNet, are in a similar kind of background, and then you go to a different image data set and the screws are on a different background, you would say that there's a domain shift in the sense that the color distribution of the pixels for a given class has changed.
Yeah. Or for instance, if all the screws in your, yeah, okay, cool. Yeah, Ben says he sees. Cool. So yeah, the two things that they introduce to try and combat this are something they called SimCLR episodes and this new architecture, cross transformers. So we start with SimCLR episodes, I think. I'm just trying to think if we need to talk about this anymore.
If I can add a little
Yes,
bit to domain shift. So I think that they explain it very well in page 6. So they say that in Cocoa, for example, in the Cocoa dataset, many of the classes are similar to ImageNet, but for example, in Cocoa, they may be partially occluded. So your screw is not going to be a complete screw, but a partial screw. So that's one type of domain shift.
Cool, thanks, Carlos. Yeah. Okay, so yeah, they go into a little bit more detail about prototypical nets and what it means to train something episodically, I suppose, or test it episodically here. But yeah, the thrust of self-supervised training with SimCLR is to do away with some of the episodes that come with the metadata set itself and basically add some new labels and some new data. So they take 50% of the episodes and convert them into what they call SimCLR episodes. And they make each image its own class and randomly augment it quite a lot of times to create a new episode. Basically, you have this support set that you've randomly you've augmented using SimCLR, and it's just the same size as the support set in the original episode. Sorry, let me get this right. So they're transforming each image in the original support set and then generating query images by sampling other transformations for the same support set. Okay, so the support set will now contain one image from each class, right? Because each image is a class in this situation. And the query set now transforms those images in a different way. But will retain the S classes because they're just samples from the original support set. So they get rid of the query set, and what you're trying to do is make your embedding from your prototypical net a bit more agnostic to sort of translations or cropping. So if there was some kind of occlusion, like Carlos says, or like the screw moves off the edge, your embedding would be more and they then reframe the loss for prototypical nets with this in mind. So let me get this right. So this I think this becomes now the distance between the one augmentation and another of the same image. And so you're trying to reduce that distance. So that's one training method that they put forward. And the other novel part of this paper is the cross transformers part. So this is sort of an addition at the end of.
Before you move on to this second, this is sorry, I have a longer name at the moment. Okay. Could I just ask a question to see if I understood?
Absolutely, yeah.
So it sounds like what they're doing is you train for a while and you're training for your specific production task, really. You take a little pause because you're worried that you're going to, lose the ability to identify features that may be useful for other tasks. And then you train for a little bit with a different set of classes, a subset of the images that you were working on before and the set of transformations of them. And the transformations are all an element of the class, the class of the image that they came from. And then and then you sort of wash and repeat. So you just, you train for a bit, you take the pause, you do this bit to sort of avoid over specializing, and then you continue. So is that the correct understanding?
I think that's a good intuition of it, because as you say, you have these categorization episodes, so that's where you're training to discriminate well between images, and then what they call SimCLR. So the MD categorization episodes are, your standard classification tasks, and you're trying to get embeddings that are good at discriminating between these classes. And then the SimCLR episodes, I think ensure that you're good at discriminating between images inside a class. So you're not losing too much in terms of spatial differences between the images, or background colors, whatever it is. That's my understanding of it. I don't know if that rings a bell, Adam. Does it?
Yep. No, this seems right. It seems in the category of, it seems like it wouldn't be hard to augment basically many training loops with a little bit of it.
Yeah, you can see it as a type of regularization.
Yeah.
It's a bit of a regularization technique.
Okay, cool. Are there any other questions about this portion, or things that people want to raise? No. Okay. So we can then talk a bit about this architecture they propose, cross transformers. So this is basically trying to borrow some of the attention mechanisms from transformers to relate a query image to an image from the support set, basically, or areas of the query image to areas of an image in the support set. And the foundation of it, I guess, is a basic prototypical net that we've just talked about. So they're using the convolutions and the spatial element of a prototypical net, but instead of pooling everything at the end, you retain some spatial information by removing this pooling. And so we end up with an embedding that has spatial information retained. And so that's captured, by the shape of this embedding here. So the way that they talk about it in the appendix, they actually pre-train this on the training set in the way that's described above for the prototypical nets on their own. So they've got this prototypical net, they've stripped off the final pooling layer, and then they introduce the key value and query heads from transformers. And it's in an attempt to get the network to pay attention to particular areas of the support set image for a certain class, right? So we have these linear maps here, this one, and this one, and they map from, so these two map from the support representation to a, we can see the dimensions here. So this one is mapping from the support set representation to the representation here, and to find the attention between a pixel, or not. So it's not a pixel actually. It's an area, because it comes after the convolutions. So for the area in the query image and the area in the support set image, we just do a dot product between these vectors here, and this tells us the sort of attention that we should pay to this area in this support set image for for this area in the query image. So we get that for every image in the support set and every area in the query image, and we end up with these matrices. We take the softmax across all of these matrices to sort of tell us which area of which image is the most important for us to pay attention to. And so we then construct a prototype embedding based on these attention values that we've got from softmaxing. So we construct a value matrix tensor using the value heads, and then use the softmax weights to sum across these value tensors from all of the support set images. And we get our prototype for this query.
One quick question.
Sure.
The number of embedded images that are the representatives of the classes, are they fixed? Or say if say there's a new class that needs to be updated also, because if you say they come from the same domain, that they might be also the same problem we mentioned earlier.
So you're saying is the size of this set?
Yes. Is it fixed, and doesn't also make it much more expensive if you have more representatives, which, like, it seems there's a bit of a trade-off going on there.
I think so. It's an interesting point. This map is fixed, but we would have to calculate these these keys and values for each of the images in the support set. I'm not sure that they're fixed. They don't mention it, or at least I haven't seen that they mention it. So perhaps, yeah, for the larger the support set, the more expensive this becomes.
It also then depends on the number of classes, right? So if you have many classes, that grows at least square. Yeah. Okay. Thank you.
So I think the number of classes is not going to make a big difference here. But what is going to make a difference is that if you want to process all the support set for a given class, then it matters how many examples you have in that class, which you should know in advance because you create the support set before, right? I think one thing about this diagram is that it looks a bit different, but it is exactly the same architecture as the transformer encoder. It is just trying to show it in 3D. So it's trying to show that it's processing images rather than one-dimensional embeddings.
Yeah.
So the embedding of an image is going to be a 2D embedding, whereas the embedding of text is 1D. So it is trying to show that, which is why it looks a bit convoluted.
I think it is important to these maps are from like one bit of the query image to one bit of this representation, right? So it is a bit different.
So if I seem to remember, just one moment.
So the maximum of the attention would be then on the maximum, say on the maximum of the representation. I mean, say you have a feature of a dog or a picture of a dog, and one head, say, finds the snout as the attention. And now what happens if there is not a corresponding feature in the feature set? Does the attention just spread out evenly across the whole thing, or?
So that's what the transformer is going to do. Is it's going to learn all the attention weights, right? So if you look just a bit down, you have your key head, not just where you were before. So the key head is a linear mapping from D, which is your number of
Internal dimension.
So you have height, width, and then D is the number of channels?
It's yeah. Well, it's not quite the number of channels. It's the third dimension of the embedding.
So in any case, you're going to be transforming that dimension. You're going to be putting it into the dimension of your model, or like what the transformers call the model dimension, right? So H and W are actually preserved by this gamma mapping. So you just do it across one dimension. I guess you have
say,
H prime, W prime.
Hmm.
So you have all those learnable weights to preserve. So each pixel in H prime, W prime is going to have a different weight for the linear mapping, and you're going to learn all those weights. Same for the value head. You're going to, this lambda transformation is going to learn all the weights that convert that D dimension into the model dimension. And same for the queries.
But isn't this map the same for every?
Yeah, it's a learn map, right?
Yeah,
it's your initial linear mapping that converts your input sequence into the transformer dimension.
Mm-hmm. But we're not learning a different set of weights for each position, are we? We're just learning one set of weights for all the positions.
Oh, I thought it was one for each position, but if it's the same, it's similar, right?
Mm-hmm. My reading of it was that it was the same.
Okay. Yeah. Okay.
But yeah, like you say, it's pretty much the same as a transformer architecture. I'm not sure what the cross was referring to be honest. I don't know if anyone has any sort of intuition on that.
Which cross?
Like, what is the name cross transformers referring to? Is it this cross?
Probably. So because you're using this sort of idea that transformers can process two sequences at the same time, right?
Mm-hmm.
But what they're doing is they are computing. So they're doing the embedded transformation for all images in the same class. So see this gamma, it's working on the support set for the whole class.
Yeah.
And then you're combining them somehow within your transformer architecture. So I guess that's so you're learning, I guess, how to you're learning the weights for the whole class at the same time.
Okay. Yeah. Yeah.
This looks very resource intensive, by the way.
Mm-hmm. It does. Because as Arvid said, you'd have to. So we're making this prototype for class C based on all of the images in the support set for class C, but then we have to do that for also for class all the other classes, right? So that we can get our query aligned prototype.
Yeah, because the transformer is calculating the centroid basically. So
you have to make it line up with the image. Yeah. So yeah, I guess the last bit to mention is this is the distance function they use. So they collect all of the centroids for their different classes, and then they calculate this query image value using the same linear map that they used before, and whichever has the smallest distance, right, is the one that you classify this image into. But you're right, it does look very resource intensive because of the amount of things that you would have to do, even the amount of linear calculations you'd have to do, even at inference time, is large, right?
Yep.
Yeah. Okay.
I'm not entirely clear how this works at inference, because I can see how they find the prototypes for training, but I'm not sure how they find the embedding at inference. Maybe you can.
So I think this is how they get the embedding at inference time, right? So they are training this as well. That's the difference. Perhaps that's not the bit. That's the bit that you're not seeing. That they train the prototypical net in tandem with the rest of this stuff.
Yeah. Okay. Okay. I see now. Okay. So you have a prototypical net giving you an embedding, and then a transformer processing all the embeddings to give you the prototype.
Yep.
So at inference, you just get the output from the prototypical net.
Yeah. So you would have to run this for each of the classes and get several query aligned prototypes, and then you run your prototypical net for your query image and pass it through the value head, and then do the distance calculation. I think.
Okay.
So yeah, I can see now that would take probably quite a lot of compute, but hopefully that sort of helps people understand roughly what's going on in that diagram. I don't know if there are any questions following that. I don't see any hands, so let's go to the next bit. Okay, so let's look at this quickly now, because I think it's interesting. I don't want to run out of time. This is basically a visualization of the first part of this structure. So we're seeing where the attention for a query image is being directed in the support set images. So we take this query image and we're looking at the highlighted sections of it. I'm not quite sure how they managed to, but I suppose it's possible to go back through the ResNet convolutions, and so you can see where in the support set the attention for these areas has sort of spread out to. So yeah, you can see that they do correspond to relevant sections of these images, right? Like sort of hand finger area of these banjo players is the same. It is being given attention to for this particular area of the query image, and it's similar for kind of all these other images.
It would have been interesting to see the previous examples they gave on like the the knot and the Gila monster, and what the transformer would say about this. I'm pretty sure it would also find some parts that look very similar. And
I'd also kind of be interested to see what the attention is being given to for support set images that aren't the same class as a query.
Yeah, certainly.
Yeah, it'd be interesting to see that, but I don't think they really show that. At least I didn't read it. There may be something about it in the appendix. Okay, cool. So they then talk about the experiments they ran. So they revisit metadata set basically, and talk about the training, how they do the training. So here we go, Arvid. The support set is not consistently sized.
Gotcha.
So I guess training time and inference time changes depending on how big your support set is. And they talk a bit about the sort of foibles between different problems within the set. So they say ImageNet has a fair few classes that represent different birds, and so you can you stand a better chance of generalizing to a test data set like this birds data set. Whereas the test data set aircraft has lots of different classes within it, but there's a single corresponding class in ImageNet. So you don't stand as good a chance of generalizing without more in the way of some kind of regularization, similar to what they talked about earlier in the paper. And yeah, basically they're saying there's a lot of different problems encapsulated within metadata set. Okay, here we go. I knew it was in there somewhere. So the prototypical nets that they've looked at in the past are relatively small. And so they talk about that not sort of lending itself to their solution very well. They need to have a lot of spatial information. And so they make their sort of base implementation of the prototypical net uses 224 by 224 input images and a ResNet 34. So they sort of back up this choice, or they talk about this choice here. And they're kind of saying that they improve things by making these changes, but not by very much. So the changes alone aren't enough to explain the improvement. But when they include their episodes, you see much better performance. So I think that's what they're trying to highlight in this table. And then, so yeah, this is basically the SimCLR episodes section, and you can see that the SimCLR is increasing performance. And then the other section is the cross transformers results. So they do it both using cross transformers on their own, and then using SimCLR episodes as well. And well, we can see that you're getting the best performance, 10% better performance than the sort of state of the art from before. From down in this section using cross transformers. And I guess some of the interesting things to point out, they point out that, or this is in keeping with what we talked about earlier with being easier to generalize this birds data set than the aircraft data set, this discrepancy here. The texture data set, so this DTD is a data set of textures, and they say that the fact that they don't see much improvement in this data set based on previous states of the art is kind of expected, because you're not getting much improvement, or spatial information is not helpful when you're identifying textures. That's what I'm trying to say, sorry. But you can also see that the adding the SimCLR episodes is helpful in pretty much all the cases. So this way of regularizing is helpful even when you're using this cross transformers architecture. They talk a bit about augmenting further and using linear regression, I think. Yeah, I'm sorry, I can't quite remember what they're doing here. A logistic regression at the end. They don't go into much detail about that, so I'm not quite sure why they do that. But
so it's instead of doing a distance-based classification, you do logistic regression.
Okay, based on your embedding. Okay, makes sense. So yeah, getting even more resource intensive, I suppose. But
I mean,
I guess it's
to
not.
be honest, to put a logistic regression layer on top of a transformer is a negligible amount of extra weight.
It's true. It's true. Drop in the ocean, I suppose. So yeah, I guess they're doing that to point out the improvement here most of all. And so this is the paragraph where they talk in more detail about the textures data set, and again they talk about this occlusion and interclass variation. So they are basically saying there are limits to this, how far we can generalize and how well we can do it. And they basically say we need to work further to understand this better. So yeah, I thought it was an interesting paper, and they clearly got some nice results. It incorporates a lot of the ideas that we've been talking about in previous weeks about attention and transformers. And yeah, I think generalization from image classification problems to other image classification problems is something that people are focusing on a lot at the minute. So it's nice to see a paper where they can make pretty good strides, I think, with how well they're doing with that. Okay, are there any further questions?
I have a comment about the paper, which is so I think the one thing that they missed was doing a bit of an ablation study on the architectures that they are combining here.
Mm-hmm.
because you're comparing. So for example, you have a transformer, which is such a big architecture, and you're comparing it with a prototypical net, which they implement with ResNet 18.
Mm-hmm.
So the ResNet 18 has so much fewer parameters with respect to a transformer that it would be interesting to understand if you actually need to use this kind of network to do the embedding, so you can so do a simpler type of embedding. Or I mean, I understand that of course the transformer cannot make the embedding for you, like you need to provide an embedding to the transformer, but sort of do you need, like, can you spare resources in making something a lot simpler for the embedding and just let the transformer do all the heavy lifting? Open question.
So just to talk to your point quickly before the question, I think you do need to at least convolve to get your embeddings, right? Because otherwise you're losing the spatial information that the whole point of this transformer architecture is to retain spatial information. And so I guess it wouldn't be super simple to get some kind of embedding that does that. I can't think of a simple way.
Well, the interesting thing about images is that I mean, I'm going to say something a bit out there, but I mean, inherently they don't need an embedding because they're already in the numerical space, right? So you could, in theory, if you, I think that one step that they could have taken is just provide the image to the transformer and see if the transformer can figure out the embeddings on its own.
Yeah, that was kind of my question too, in a sense. That's from the paper we read a couple of weeks ago, 2 weeks ago maybe, right? Was kind of doing exactly that. It's like, forget about the ResNet, just throw the image in and see what happens. And, you know, it maybe took a little bit more time to train to convergence, but it seems to have kind of worked.
Yeah, I think that's an interesting point. Definitely.
I would have another question, if I may.
Yes, cool.
So we do have a representation dimension, right? So the representation itself does live in its own space. Right? And we do some distance-based measuring in that space as well. So how close is the query to other elements in that space? Now, wouldn't we expect that this works better if we have lower dimensions in space, or at least be sensitive to dimension? Because if I remember correctly, like things like nearest neighbors generally work different in different dimensions.
So I think the distance function is happening in this dimension, in this representation space. So are you saying that the higher the dimension, the more difficult it is to find nearest neighbors?
I think, if I remember correctly, the more susceptible you are to noise, because you simply have more dimensions where a single dimension that is slightly off can throw your nearest neighbor off.
I can believe that.
Yeah, I think that one of the papers, I can't remember whether we've read earlier, but I guess the summary was with enough dimensions, right, everything is close.
Yeah.
Yeah. Yeah, I wonder if the way that they are calculating this distance metric would help with that.
No, actually, L2 distance will probably just make the problem worse. But that's one cool thing about the transformers is that you can play with your model dimension. So you could so because this dk, dv, and dq are well, they use the same dimension for keys and queries. Oh, they have to. Because you can tune that dimension to whatever you want, I think you should be able to mitigate that problem.
Yes,
so you ending up with a tensor that's height and width of the original embedding times the size of the value, right?
I think so, yeah.
Yeah.
So you sum over all the x, y directions as well, right? When you calculate the proximity.
Yes. Yes. Yeah, that's encapsulated within here, I guess.
Yeah. Thanks.
But yeah, I imagine it would probably be quite difficult if these values were large. Yeah, would be more susceptible to noise if like V was large. Cool. And one question from Adam was, will it change your practice or what you do? I'm not sure that it will change NPLAN's practice, at least not in the near future.
Yeah, we don't really concern ourselves with images very much, but I think that even in the image processing field, this is also somewhat niche. So you're trying to generalize from one data set into another data set. So to be honest, I don't think it's breaking enough so that suddenly this is going to become the industry standard.
The one thing that really spoke to me, I think, in it was around the, sort of another data point suggesting that doing something like SimCLR can be quite helpful.
Yeah, I would expect something like what we saw last week, like the vision transformers, to be a bit more disruptive on this, because it's a completely so it's not that you're building on a previous architecture, but you are just proposing to use something entirely different. You're saying you don't need convolutions anymore. Here you still need convolutions and then put a transformer on top of that.
Yeah. Cool. Any further questions?
Cool. So we've come to the end of the time for this. So if we can all thank Dan for the very interesting discussion that he brought to us today, we can do with show of hands. I think Dan can see the show of hands.
Thank you very much, Dan. That was very good.
Thank you.
Yeah, thanks very much. As usual, we would like to invite all of you to send us emails if you want to present a paper or if you have a topic in mind. My Zoom just froze, so I can't really see the results of the poll or stop the recording. Dan, I don't know if you can stop the recording.
I can probably stop it. I don't know if I can stop the recording. Actually. No. I also can't close the poll. So
this will be interesting. Okay, so well, thanks everyone for joining, and we'll see you next week.
thanks everyone.
Thank you. Cheers. It was good.
Yeah, bye-bye.
I don't know what we're going to do, Carlos.